Imagine your morning commute for a second. You're walking into the station holding your transit card, right?
Right,
You step up to the turnstile, tap the plastic against the reader, and beep,
right.
the gates just slide open. You don't even break your stride. You're just seamlessly joining the crowd, flowing toward the trains.
Yeah, I mean, it feels completely frictionless by design. For the person swiping, the experience is almost, well, it's binary. The gate opens or it doesn't, and you just move on with your day.
Exactly. But behind that single beep is this hidden, massive, sprawling digital universe. And today, we are taking a deep dive into the invisible mechanics of that exact world.
Which is fascinating because the infrastructure required to make our world feel that seamless is absolutely staggering.
It really is. And to uncover how it all operates, our roadmap today comes from a comprehensive CS50 lecture slide deck on database scaling and SQL. We're looking at a huge stack of architectural diagrams, technical specifications, and some really cool real-world case studies.
Yeah, we are going to explore everything from the Massachusetts Bay Transportation Authority, the MBTA transit system, all the way to the Museum of Fine Arts in Boston.
It's quite the range.
It is. And the goal here is to demystify how these massive applications and systems that you use every single day actually function under the hood.
Right, like how do they store your personal info without losing it?
Exactly. How do they survive massive, unpredictable spikes in user traffic without completely crashing? And, how do they guard the vault against malicious hackers?
Because we tend to think of databases as just dry, endless spreadsheets sitting on a dusty server somewhere. But they aren't static spreadsheets at all. They are bustling, highly engineered cities of information.
With their own traffic laws and zoning boards.
And security forces. So today, we are going to make that invisible digital city visible for you.
Because every time you interact with the digital world, whether you are swiping a transit card or liking a photo, you are triggering this massive chain reaction in these architectures.
So, okay, let's unpack this. Before a digital city can grow to serve millions of commuters without collapsing, it has to be built perfectly at the microscopic level, right?
It has to be airtight, yes.
We have to start with how data is actually packed into the system. And looking at our sources, the MBTA and their Charlie Card Transit Pass serves as a fantastic foundational example.
Yeah, so in the database world, when you are building the foundation for a massive system like a transit network, two of the heavyweights you will constantly hear about are MySQL and PostgreSQL.
The big names.
Right. These are the relational database systems doing the heavy lifting. And when engineers use these tools, they organize everything into a schema, which is a very strict, uncompromising structure.
So for the Charlie Card system, we are looking at three main interconnected tables.
Exactly. First, a card table that just contains a unique ID. Second, a swipe table tracking the type of swipe, the date time, and the financial amount. And third, a station table with its own ID, the station's name, and the transit line it belongs to.
And taking a look at how these tables are built, picking the right data type for each column feels exactly like packing luggage.
Oh, that's a good way to put it.
Like if you are going away for a single weekend, you don't pack a massive steamer trunk. It takes up the entire trunk of your car, it's heavy, and you're mostly just transporting empty air.
Yeah. And in database terms, that steamer trunk is a data type called a bigint, a big integer.
Right.
It takes up 8 bytes of storage on a physical hard drive, and it's designed to hold astronomically huge numbers up into the quintillions.
Which is massive.
Yeah, so if you are logging something massive, it's indispensable. But if you only need to store a very small number, you use a data type called a tinyint.
Which takes up just one single byte of storage.
Just 1 byte. I mean, a tinyint can only hold numbers from -128 to +127, or 0 to 255 if it's unsigned, meaning it doesn't go below 0.
So if an engineer gets lazy and uses a bigint steamer trunk, where a tinyint would do the job,
The system wastes 7 bytes of space per record.
and 7 bytes sounds like nothing.
It does, but multiply that wasted space by millions of Charlie card swipes every single day over years and years, and suddenly the database has wasted terabytes of incredibly expensive server space for literally no reason.
Wow. And conversely, if you pack too small, like if you try to shove the number 300 into a TinyY NET that only goes up to 255, your items literally overflow the suitcase.
Exactly. The database encounters an integer overflow, which can lead to corrupted data or just a complete system crash.
It is wild to think about how manual that process is. Someone actually has to sit down at a keyboard and decide the exact physical size of the digital box for every single piece of information we generate.
It's foundational engineering.
But wait, I do have to push back on a concept in these slides. When it comes to real numbers, specifically decimals, the source material draws this incredibly hard line between a float and a decimal.
Right, the floating point numbers.
It explicitly says float has, quote, floating point imprecision, but decimal offers fixed precision. Wait, so math inside a computer can just be imprecise? Why would anyone ever use a float if it gets the math wrong?
I know, it sounds totally counterintuitive to the way we think about computers. We assume a computer is just a perfect calculator. But it really comes down to a necessary trade-off between blazing computational speed and absolute accuracy.
Okay, so speed over perfection.
Yeah, a float is a mechanism for a computer to calculate complex fractions and decimals incredibly fast by basically estimating them. The processor doesn't store the exact number, it stores an approximation.
So where would that actually be useful?
Well, for something like the physics engine in a fast-paced video game, an estimate that is 99.999% accurate is perfectly fine. The math is lightning fast, the geometry calculates in real time, and the graphics run smoothly on your screen.
Well, that makes sense. But I'm guessing mostly accurate is entirely unacceptable when the numbers you are calculating represent actual money.
Exactly. When you are looking at the amount column in a Charlie card swipe, floating point imprecision becomes a massive liability.
Right, you can't have a commuter's transit balance randomly lose a fraction of a cent every time they swipe.
Because that would compound over months until eventually their card declines incorrectly. So for financial systems, engineers use decimal. A common configuration is decimal 5, 2.
And if I'm reading the syntax right, decimal 5, 2 means the database reserves space for a maximum of 5 digits total, with exactly 2 of those digits strictly positioned after the decimal point.
Got it. So the maximum value that specific column can ever hold is 999.99 or negative 999.99.
It strictly enforces financial accuracy.
Yeah, it takes more raw computing power and storage to process than a float. But for handling currency, that fixed, uncompromising precision is just a strict necessity. The math must be perfect.
So our digital luggage is packed perfectly, and we have the right data types assigned. But once real people actually start interacting with the system, how do we enforce the rules of the world?
What do you mean?
Like, how do we make sure someone doesn't hack their transit app and somehow log a transaction that says they swiped their card to buy a slice of pizza instead of a train ride?
Okay. This brings us to the concept of data constraints. You have to explicitly tell the database what is and isn't allowed to exist in a given column before the data even arrives.
Setting boundaries.
Yes. And one of the most effective tools for this is an ENUM type.
An enumeration. Looking back at the MBTA swipes, the type column is restricted by an ENUM constraint, so it can only ever accept 3 specific text strings: enter, exit, or deposit.
Exactly.
So if a glitch in the reader, or a hacker manipulating the app, tries to insert pizza into that column, the database looks at its allowed list and literally rejects the action at the door. It refuses to save it.
It creates a rigidly closed universe of possibilities.
Right.
But enforcing rules on a simple turnstile swipe, where the options are just enter or exit, is relatively straightforward. What happens when the data you are trying to protect and manage is a complex, priceless, historical archive?
But that is a whole different ballgame.
It is. So to understand how databases handle complex logic, let's look at the Museum of Fine Arts in Boston.
The MFA. The slide deck pulls data from their actual collections. We're looking at intricate records for specific pieces, tracking artwork titles like Farmers Working and Peonies and so forth.
Yeah, and when you have a massive museum catalog with moving pieces, loans, acquisitions, and restorations, you can't just rely on a simple enter or exit rule.
Because there's too much going on.
Right. Managing that requires stored procedures. A stored procedure is a predefined block of SQL code, basically a script that is saved directly inside the database itself.
Okay.
Imagine the administrative steps required when the museum moves a priceless painting from the vault to a public gallery. The system has to update the painting's location, change its public visibility status, log the employee who authorized the move, and update the insurance records.
That's a lot of separate steps.
And if a programmer writes an app that sends those 4 separate commands over the network one by one, there is a massive risk. What if the network drops after step 2? The database is now totally out of sync.
Oh, I see. So instead of the app sending 4 separate instructions over the internet every time a painting moves, the database already has the instruction manual saved internally.
Exactly.
The app just sends one tiny message saying, execute the move art procedure for painting ID 402, and the database handles all the complex steps internally. ensuring they all succeed or fail together.
Which is brilliant because that reduces network traffic and eliminates a huge margin for error. That internal consistency is vital.
Definitely.
And what's fascinating here is the MFA example reveals another layer of how enterprise databases maintain their reality. The concept of soft deletes.
Right, the invisibility cloaks.
Yeah. According to the architecture in the slides, the MFA database does not actually delete records when a piece of art is permanently removed from the collection.
It doesn't.
No. Instead, they altered the table structure to include a single column named deleted. It acts as a binary flag. A 1 means the item is deleted, and a 0 means it is active.
So when a patron or an employee looks at the current collections on a screen, the system just silently filters the view. It runs a command, select star from collections where deleted equals 0.
Exactly.
So wait, when I delete an old embarrassing photo on my phone or a text message, it might not actually be gone off the server. It is just wearing a digital invisibility cloak.
In massive enterprise systems, true deletion, like wiping the data off the physical hard drive, is incredibly rare.
That is slightly terrifying.
Well, think about the historical and relational integrity of a museum like the MFA. If a painting is sold to another gallery or tragically destroyed in a fire, the administration wouldn't want to just hit a delete key and permanently obliterate all record that the museum ever owned it.
Like where they acquired it or how much they paid for it?
Right. It would be the equivalent of burning their own history books just because a painting left the building.
That makes total sense.
So by utilizing a soft delete, simply flipping that 0 to a 1 in a hidden column, they maintain the entire relational integrity of the database. The record instantly vanishes from the public-facing view. But the deep data is perfectly preserved for the museum's internal administrators and auditors.
And yes, this structural philosophy absolutely applies to a vast majority of the applications and social media platforms you interact with every day.
It does.
Like I said, slightly terrifying, but mechanically, it is incredibly clever.
It really is.
Okay, so here's where it gets really interesting. We have our digital luggage packed efficiently, and our rules are rigidly enforced with enums, stored procedures, and soft deletes.
If everything is in order.
Right. But what happens when the digital city goes viral? Let's say our transit system suddenly opens 3 new train lines, or the museum releases an augmented reality app that gets downloaded 1 million times in an hour.
A huge traffic spike.
Yeah. How does the architecture jump from handling 100 reads per minute to 100,000 reads per minute without catching fire?
Well, the architecture has to scale. Scalability is defined as the system's ability to seamlessly increase or decrease capacity to meet fluctuating demand. And historically, computer scientists use 2 different methods to achieve this vertical scaling and horizontal scaling.
Oh, I love the real-world analogy for this from the sources. Vertical scaling is like owning a family car, and when you have more kids, you just take that car to the mechanic and upgrade it into a massive 50-seat bus.
Right, you are just increasing a single server's raw computing power. You pull the machine out of the rack, shove in more RAM, upgrade the processors, and turn it back on.
But horizontal scaling is an entirely different philosophy. That is like realizing the bus is getting too slow and expensive, so you just buy a massive fleet of regular cheap cars.
Yes, that fleet of cars is horizontal scaling. You distribute the computational load across multiple, smaller servers. You aren't building an expensive supercomputer. You are coordinating an army of standard machines.
But if I own a fleet of regular cars, how does a passenger know which car to get into? Do we need a dispatcher?
You hit on the crucial missing piece. In a horizontally scaled system, you use a load balancer. It acts as the dispatcher standing in front of the fleet.
Yep.
When 100,000 users open the app at once, the load balancer looks at the servers and directs traffic, saying, server A is busy, send this user to server B is full, send the next to server C.
But to make that fleet operate cohesively, you need replication.
Exactly.
Because if I get into server B needs to know exactly what is happening on server A.
You have to keep exact, synchronized copies of your database on multiple servers so that no matter which node the load balancer assigns to a user, they see the exact same information.
And the slides get surprisingly funny to explain how this actually works.
Oh, the Grumpy Cat slides.
Yes. To illustrate replication models, specifically the single leader model, also known as leader follower the lecture, uses repeated images of the internet meme Grumpy Cat.
It is a memorable way to visualize the hierarchy, honestly. In a single leader model, one database server is the Grumpy Cat in charge. That is the leader. All the other servers in the fleet are the followers. The leader is the only node allowed to take new incoming data, what we call writes. If you change your password or deposit funds, it goes directly to the leader.
And then the leader has to share that.
Right. The leader then has the immediate burden of turning around and passing that new information down to all the follower nodes, which are typically read replicas.
Servers dedicated solely to letting users view data without changing it.
Exactly.
So the cat is grumpy because of the sheer stress of middle management. It is constantly catching incoming data and shouting instructions at the followers.
It is the heavy burden of network delays, really. The leader node is constantly stressed because it has to decide how strictly it wants to manage the sharing of data. It has two choices, synchronous or asynchronous replication.
Okay, so if they are asynchronous, does that mean my transit app might show my balance as $0 for a few seconds right after I deposited $20? Just because the follower server I'm looking at hasn't caught up to the leader yet?
That is the exact trade-off. In asynchronous replication, the leader receives your $20 deposit, shoots a quick memo across the network to the followers saying, update this, and immediately confirms the transaction on your phone without waiting to see if the followers actually received the message.
So it feels incredibly fast for the user.
It does. But as you deduced, for a few milliseconds or even seconds if the network is congested, some servers think you have $20 and some still think you have $0.
And if I happen to be reading from a slow follower node, I panic because my money is missing.
Yeah, navigating that temporary lag is one of the most difficult challenges in scaling.
What's the alternative?
The alternative is synchronous replication. The leader gets your deposit, tells the followers to update, and then the leader literally pauses.
It just waits.
It waits until every single follower sends a receipt back saying, got it, updated. Only then does it tell your phone the transaction is complete. It guarantees perfect accuracy across the entire globe, but if one server in another country has a bad connection, the entire system lags. Every user waits.
Oof. And if even a sprawling fleet of replicated servers isn't enough to handle the sheer volume of data, the slides introduce a concept called sharding.
Sharding is fascinating.
Which, sticking to our analogies, is like walking into the Department of Motor Vehicles. Instead of one massive, demoralizing line for everyone in the city, you walk in and see different lines based on your last name. One desk handles A through I, one handles J through R, and one handles S through Z.
That's a great comparison. Sharding literally slices a massive database into smaller, distinct pieces that live on totally different servers.
That's not just making copies anymore.
No, it handles immense load because you aren't just copying the entire database over and over, you are dividing the labor. The server handling the A through I users never even sees the traffic from the S through Z users, freeing up immense processing power.
So what does this all mean? We've scaled horizontally, we have dispatchers routing traffic, we've sharded the data, and we have an army of grumpy cats processing thousands of transactions a second across the world.
We've built a massive digital city.
We have this massive, interconnected, globally replicated digital city, but a larger surface area inherently means a bigger target for malicious actors. If data is flowing everywhere at once, how do we protect the vault?
This is where the architecture shifts to security protocols, specifically access control and the threat of SQL injections.
Right.
The absolute first line of defense is simply defining who is allowed to do what. Database administrators use hard commands like create user and then carefully assign privileges with grant or revoke.
Okay, so you might grant a new third-party app the ability to select, meaning it can read public data, but permanently revoke its ability to insert or delete records.
Exactly. But hackers don't usually wait around for an administrator to grant them permission.
No, they don't. And the slides walk through a terrifyingly simple attack called a SQL injection. The example they use is something we interact with daily, a standard login screen asking for a username and password.
Yeah, under normal circumstances, when you type your credentials and hit enter, the database runs a query that looks something like this. Select aid from users, where username equals Carter and password equals password.
Just a basic check.
Right. If both the username and the password match the records, the database returns your ID and you get in. But in a SQL injection, a hacker exploits the fact that the database is blindly reading whatever text you type into that little password box.
So the hacker types this exact bizarre phrase into the password box, quote, password or 1 equals 1, unquote.
The syntax itself is the weapon.
How does the database interpret that input?
Well, because once that phrase is injected into the query, the database isn't just reading it as a password anymore, it is reading it as executable code.
Oh, wow.
Yeah, the database evaluates the logic of the entire sentence. It says, okay, does the password match? No. OR is the number one equal to the number one. Well, one is always equal to one. That is a fundamentally true mathematical statement.
So the database evaluates the entire statement as true. It shrugs and just lets them log in as the user Carter without ever knowing Carter's real password.
Exactly.
It is exactly like handing a bank teller a deposit slip where your name is written as John, also please give me all the money in the vault. If the teller is naive and doesn't separate your name from the instructions, they just read the paper out loud and rob the bank for you.
That is the perfect analogy. It exploits the computer's inability to distinguish between what is passive data, your name, and what is an active command.
That's wild.
And the slides also highlight the mechanics of a union attack, which uses a similar vulnerability to devastate a system.
How does the union attack work mechanically?
Imagine a search bar on a website where you type in a product ID to see its price. The hacker types in a valid product ID, but then adds the SQL command union, followed by a malicious command like select id from accounts.
Oh,
Yeah. The union command literally tells the database to execute the first search, execute the second search, and glue the results of both tables together into one output.
so the database innocently returns the price of the product you asked for, but glued to the bottom of the screen is a list of every single private account ID in the entire system.
Which is a catastrophic data breach.
So to stop this, what do engineers do? Do we just write code that aggressively locks down the specific characters a user is allowed to type, like forbidding things like equal signs or the word union?
You'd think so, but if we connect this to the bigger picture, trying to ban specific characters is a losing game. Hackers always find workarounds.
Right, they just use different symbols.
Exactly. The true solution requires fundamentally changing how the database parses incoming information from the outside world. The industry standard is utilizing prepared statements.
Syntax in the slides is prepare name from statement, followed by an execute command.
Yes. What a prepared statement does is force the database to rigidly, permanently separate the code from the data. Think of it like pouring concrete. The database draws a literal, unchangeable blueprint of the query first, setting the structure in stone. It uses a placeholder, usually a question mark, where the user input will eventually go.
I see.
So the database compiles this blueprint and says, I'm going to check a password now. Whatever the user types next is strictly passively data. It cannot, under any circumstances, alter the structure of this blueprint.
It puts the incoming data into a secure quarantine box before it is allowed to interact with the database logic.
Precisely.
It completely neuters the 1 = 1 trick. The computer doesn't evaluate the math, it just looks at the entire phrase, sees it as one long, incredibly weird password, realizes it doesn't match the record, and denies entry.
It strips the text of any executable power. The structure in the database is entirely protected from the chaos of user input.
What we have covered an incredible amount of ground today.
We really have.
We started by packing the absolute smallest byte of data, a TinyInt representing a single transit card swipe. We learned how museums and enterprise apps hide rather than destroy their history using the invisibility cloaks of soft deletes.
The hidden columns.
Yep. We scaled our servers out from a single bus into a massive, globally distributed fleet of Grumpy Cat-led nodes. And finally, we locked down our digital city against SQL injections by putting user data in structural quarantine.
It really highlights the beautiful, invisible complexity of our daily lives, The layers of architecture required to make a simple tap of a card feel immediate and safe are just a marvel of modern engineering.
So the next time you step up to a subway turnstile and tap your card, remember you aren't just hearing a simple beep. You are triggering a massive, globally replicated, fiercely guarded symphony of data.
A symphony that is executing complex stored procedures and balancing loads across fleets of servers thousands of times a second, all day, every day.
But before we go, there is one final thought that is going to linger with me from these sources, combining two different concepts we discussed.
Ooh, what's that?
Well, we learned today about soft deletes, where your deleted data isn't actually erased, it's just flagged with a 1 in a hidden column to become invisible to you.
Right.
And we learned about horizontal scaling, where that data is constantly asynchronously copied and replicated across a vast fleet of servers all over the globe just to handle user traffic.
Yeah, the architecture demands that the data is hidden rather than destroyed and heavily duplicated rather than centralized.
So if your personal information is rarely truly deleted by the systems that collect it, and it is continuously being copied across a fleet of global servers you can't even see, is it technically impossible to ever fully scrub your digital footprint once it enters a truly scaled database system?
Oh, wow. That is a haunting implication to walk away with. Once the data enters the network, it basically belongs to the architecture.
Something to ponder the next time you hear that turnstile beep. Thanks for taking this deep dive with us. See you next time.